welcome to this session which is on latches and flip-flops. So far, all the circuits we've been looking at had no memory. They are interesting, but then they can't do anything very useful. For you to begin to actually do useful things, you need to be able to build circuits that can remember. Because computers or the electronic devices or digital devices that you come across today need memory to be able to work. So if you can't remember anything, you can't build circuits that remember anything, then it's not too useful to you. So the circuits that can remember things are known as sequential circuits as opposed to combinational circuits that we've been looking at previously. So combinational circuits, those that don't have memory, and sequential circuits that have memory. And the basic building blocks of sequential circuits are latches and flip-flops. So what we need to do, or be able to do, is to see how these flip-flops or latches operate. A very fundamental one is the SR flip-flop, the D and the D latches. So you should be able to explain how these two work. So we'll look at an inventor with feedback, the set and reset latch, which is the SR latch, states gated latches, D latch, and then the S and R flip-flop. So we'll look, these are the things we want to look at, or you should know by the time you complete this session or studying this session. The recommended test is the Fundamentals of Logic Design, Chapter 11. Most of the material you find there. But again, you find a lot of material on the net on this, and I recommend that you watch some of the videos on the net on the S and R flip-flop design. So let's look at the inventor with a feedback and how it helps us to obtain memory or remember things. Look at that. You have an inventor, right, which is connected to an inventor and then sends back. Now, in the circuit shown, suppose that at some instant of time, the inputs to both inventors is 0. Is this a stable, condition? What do you think will happen, right? What do you think would happen when both of this is 0? Is this stable? Can this be achieved? Now, let's have this. A simple thing, you have an inventor and you fit this back into it, right? So let's say you have a 1, right? A 1 at the input here. Now, if you have a 1 at the input here and an inventor, that gives you what? A 0. Then that goes back into giving you what? A what? A 0 here. Gives you a 1. So what do you have? You have an oscillating thing. So you have an oscillation of the input. So this will keep oscillating, right? Now, if on the other hand, right, you have this, try to analyze it. If you put a 0 here, that gives you a 1 here, isn't it? And then that 1 goes into the input of that. That gives you what? A 0. And that 0 comes back here. So what do you get? And then supposing you had a 1 at the input, yeah? And then that gives you a 0. And then that 0 then feeds into that gives you a 1. So can you see what is happening? It means that no matter what you have here, once you put something there, you are maintaining that value. That then begins to give you an idea as to what condition we can have. So that gives you an idea as to what is possible in terms of memory or recalling things. Right. So now let's look at this. So here, the key idea here is that you are having feedback. You are feeding back. You know, whatever you had as an output, you are putting it back as the what? Input to the circuit. So you have an OR gate here. Yeah, it's a NOR gate because you have inverted it, right? So you put a 0 here. You feed it with a 0, right? So once it's a 0, 0 or anything, yeah? Because since it's an OR, yeah, you would have a 1 there. Now, if this is a 0, a 1, or a 1, yeah, would give you, because of a 1 there, you invented it, that gives you a 0. So the 0 will come here at the output. So you can actually go through this circuit and analyze it. So if there's a 0 here, what happens? So if the S is 0, what happens? If the S is 1, what happens? So if the inputs S equal to 0, equal to R equal to 0, the circuit can assume a stable state, yeah, with Q equals to 0 and P equals to 1. This is a stable condition because P is 1 and fits into what? The second gate, forcing the output to be what? 0 at all times. Now, if we change this, and put S equal to 1, right? P will then become what? 0. Now, if P is 0, right, as here, then the condition becomes unstable, right? Now, then the sort of the second circuit we didn't know where to be. Yeah, the second circuit we didn't know what, because now this is 0, that is 0. Then this then becomes 1, this goes back here, then we really don't know where we are, you know. So we have an unstable condition. This informs us as to how the S or the set and reset latch should be working. Now, if we change the S back to 0, the circuit will not change state, you know, because Q is already 1. And this 1 feeds back into the first gate, causing the P to go back to 0, to remain at 0. So the inputs, again, are S equal to R equals to 0. But the outputs are different than those we started with. So the circuit will then have 2 different stable states for a given set of inputs, right? Now, if we now change R to 1, Q will become 0, and P will then change back to 1. We then change R back to 0, the circuit remains in this state, and we are back where we started. So this is what drives the understanding of this SR state, you know, of trying to maintain a particular state. Now, a way to represent it diagrammatically is this. Yeah. So this would help you. So you can analyze that, or to attempt to analyze this. You have R, S, Q, and not Q. And then you have a feedback from not Q into R, and a feedback from Q into S. So you can then put zeros, R equals to 0, S equal to 0, and see what happens. So you go sort of work this through step by step to see how this behaves. So that would give you the understanding of the S or the set and the reset latch. Now let's look at states. To fully understand this, we need to actually understand states, that is how the condition of the circuit. So you have a present state, the next state as well. So the present state denotes the state of the Q output. That is where what Q is, the latch or the flip-flop at the time of the input signal. The next state represents what state it will take, or what form it will take after this is after it's been excited. So if Q at T is the present state, then Q at T plus E will represent the next state. So we can write a characteristic equation for this, for the next state, to be R at T, or not T, S at T plus Q at T, yeah, which would give you the next state. So the equation for the output P will be S at T and Q at not T. So then the next state will represent normally as a plus, so Q plus, and then P will be S naught Q naught. So these are the state equations, so to speak, yeah, for this. Right. These functions you can put in a truth table as well. So you have a S, R, and Q, and then the next state, right? So if you have S is 0, R is 0, right? And then Q, what is Q? Then the next state, then what it would be. And then S, R, S 0, R is 0, Q is 1, what the next state would be. Yeah, so this shows the next state map, and this is a truth table. Some inputs are not allowed, because once you have those states, you have an unstable situation. So those states are not, those inputs are not allowed. Now, there is also a gated latches that you must be aware of, and this is derived from the S and the R flip-flops. Now, how does it work? So you have your S and R flip-flop, but then you have a gate which you control probably with a clock, right? So it's the same thing, only that you have a certain, instead of having the S feeding directly and the R feeding directly in the flip-flop, you actually put it through the AND gates, right? And then what you should do now here is to try and see what happens, how this circuit would behave. So in other words, now you have an additional input G. So when you change this G, how does the Q and the P would behave upon the input values of S and R? So you can work through this state by state or step by step. So if S is 1, R is 1, and G is changing from 1 to 0, what happens, right? So in other words, you can use the G to control how the distance change states. This is what it's telling you. You can use what? The G now to control the way the distance changes state. In other words, this is a memory element, and then you can then use the G to say when it should change state, when it should change from, say, 0 to 1 or from 1 to S0. That's what the G then is used for. There's a gated latches. Now the D latch. The D latch is very similar to the gated latch, except that now you combine the S and the R. Yeah, you see the S and the R, you combine that. You combine this S and the R, you combine that, and then you invert the input to the R. So this is combined as one input with an inverter here. This D latch is normally used as a data latch. So it's one of the simplest forms of memory elements. So the data, you put in the data here and use this to control when that data is put on goes on the output. So that is what how it's done. So it's worth spending some time looking at the details of the operation of this D latch. Okay. So now the S and R flip-flop. This implementation. Yeah, you can implement it with two latches, right? So what you need to do is carefully look at the situation when S equal to R that's equal to 0, S equal to 1, R equal to 0, S equal to 0, R equal to 1, S equal to R equals to 1. So what happens for each of them? So to summarize that, when this happens, there's no change in state. When this happens, the Q, it says Q to 1, and then when this happens, it resets Q to 0, and this state is not allowed. So this is how this S and R flip-flop operates in summary. But you can find more details on this in the textbook, and you are advised to read that and be conversant with its operation. Now, a question for you to look at is how a latch can be constructed from an OR gate and an AND gate and an inverter. What restrictions must be placed on R and H so that P would always equal to Q? And then you need to construct a next state table and derive the characteristics equation for the latch. So this is something I would like you to have a look at and see if you can attempt to do it. Thank you.